Welcome back. Our last topic for today is elimination. We're going to look at biomolecular elimination on this page, and then in a couple pages we'll look at unimolecular elimination. And what's happening here is this nucleophile, instead of doing a backside attack on the carbon that has the leaving group, it's attacking a hydrogen on a carbon one away. And the reason for this is this nucleophile is also a strong base. That in and of itself does not make this an E2 reaction. If we have a strong base is half the criteria. Need E2. Need 2 parts. Strong base. Also need heat. Why do we need heat? Formation of new pi is endothermic. Pi is less stable than sigma. So processes that require making molecules that are less stable are generally endothermic. They will require heat. So we've got those two things. We'll see an alternate. Might as well point it out right now. Or just a strong and bring back an old word. Bulky base. And I'm going to give you the strong bulky bases that you'll see in this course. And I'm just going to make your life a little simpler. One of these. I'm going to limit to these, okay? We got a tertiary carbon with an O minus, conjugate base of tert butyl alcohol. And we'll do some nitrogen ones too. Kind of hard to make the tertiary version, but hey, nitrogen can have 2 groups. See, they're bulky. Isopropyls on each side. Other strong bulky bases. You'll see, I mean, they're identical. The 2 O minuses, they have a tertiary carbon attached. So really, is there a big difference? No. We could put this in a ring too. Those are E2 bases. See one of these? E2 is your conclusion. Cool. So regardless of anything we've talked about today, these would change your mind, regardless of the previous parts of the analysis. One of those will change your mind, or this combination, strong base with heat, like this and this. There's an example right here. Strong base, pKb -3. That's the definition of strong base, negative pKb. Heat, right there. And what happens is you grab a hydrogen that's on a carbon vicinal to the carbon with the leaving group. And that's a lot of words to say. From now on, I'm going to say grab a beta hydrogen. Beta hydrogen. We have to know what beta means. Do not confuse this with alpha from chapter 3 when we did optical rotation. This is a new alpha. Alpha is the carbon with the leaving group. Alpha carbon is the carbon that's bonded to the leaving group. Beta carbon is any carbon adjacent or vicinal to the alpha carbon, right? There's one. If these were carbons, they'd be beta as well. They could be candidates for E2. And a beta hydrogen is any hydrogen bonded to the beta carbon. So if you're living on a beta carbon and you're a hydrogen, you're a beta hydrogen. Simple enough. The transition state. So I hope this looks a little like this and a little like these, because that's what transition states are. They look like reactants and they look like products. So the transition between O minus and OH is O with a partial bond to H. The transition between having a full bond to carbon and no bond to carbon, because they're bonded to oxygen, is a partial bond to carbon. Transition between no pi and a full pi is partial pi. Transition between leaving group having a bond to carbon and not having a bond to carbon, partial bond to carbon. Transition between negative charge on O and neutral O is a partially negative O. That transition between a neutral leaving group and an X minus leaving group is a partial negative on the leaving group. The geometry. This reaction works best if the electrons flow away from each other. And that's best if we have the H sticking one way and the leaving group 180 degrees away. Okay. You do know you're making a pi bond, right? Do you remember what orbitals make pi bonds? P orbitals make pi. So this pair of electrons used to be in a hybrid orbital, sp3c to sh, and it's ending up as a pi bond. So each carbon needs to rehybridize to have a pi, and you don't get a pi unless they're the same type of pi, py, py. So that's what makes these have to be coplanar. They're in the same plane, HC and CX. And we want these electrons here as far away from these as possible because they don't like each other. So anti is the way to do that. And that's why we like this anti-coplanar transition state. Now in other semesters where we can go into more detail, we do examples where sometimes anti-coplanar is not possible, so the reaction doesn't proceed, or another reaction happens instead. I will not get into that. So I'm not going to make you draw this transition state, but realize the reaction works best if it's possible. Got it? And let's do a reaction where E2 would be our conclusion. And I chose sample problem 8, and then I did an alternate for 8 down here with a little editing. And I can do an alternate if you want. Yeah, let's see. Yeah, I got my alternate here. We'll finish the day with that one. Oh, we already have that. Dangerous here. I'm going to forget the order. And this be alt squared. I don't know. Alt squared. And all I'm going to do here is, let's see, what do we have? We have acetonitrile there. This is getting confusing for me. 2 pages back. There's acetonitrile. I forgot to copy it. And the alt, apparently. And keep that, but add one little thing. Here's the thing. Changes everything. Pen needs to be on. There. Instead of waiting forever, let's just go back 2 pages, shall we? 9 goes back to 11. Okay. What do we have here? Do your analysis the same every time. Don't change for strong bases or anything. Rx secondary, SN1, SN2. It's going to be good here. good here. And these should go down there. All right, we'll do the answers, and you have the blanks underneath. Let's just go with it. Nucleophile. Normally, you should say RO minus strong SN2. Go ahead, say what you're normally going to say anyway. I'm going to add the big old butt here. But also a strong, bulky base. I'd like to point out, you can't just say that about any strong nucleophile. Only some of the strong nucleophiles are strong bases, and only some of those strong bases are strong, bulky bases. So this is new. And that changes everything. E2 will win the day because of that. But don't stop. You get a point for solvent no matter what, or you lose a point for solvent if you ignore it. Solvent is ROH, polar protic. SN1 is your conclusion for that, but we already overrode everything with the E2. And as soon as you do E2, I'll give you a hint sometimes about how many products. I want 3 products here. That means organic products, not side products, not the base picking up a proton. 3 products that result from E2 on this molecule. And as soon as you conclude E2, you better be getting your Greek on. Where's your alpha? Carbon with a leaving group. Where's your beta? 1 away. What happens on the beta position? You got to remove this H. And you got to, or you don't do both. And or that H. If you do the one on the left, you get a pi bond here. I'd like to point out with sigma rotation, you'll also get the cis version. And if you have to pick major and minor, I hope you're picking this for major. It's got less steric hindrance. It's more stable, so it's major. And the most minor would be take that H off the end beta carbon, and that'd be most minor. The double bond has only 1 carbon attached to it. And that's a hyperconjugation thing. 1 bond to carbon has less hyperconjugation than the pi that has 2 bonds to carbon. The alkene that has 2 bonds to carbon. The alkene here also has 2 bonds to carbon. And that's way more stable than mono-substituted alkene. These are both di-substituted alkenes. Okay. Now, in the next one, I'm going to write down nucleophile strong SN2, and I'm not going to write any buts. Strong nucleophile favors SN2. It's not a bulky base, and there's no heat involved. I mean, if there was heat involved, which would be my 8 alternate squared, if you were paying attention, I will have the one with heat involved. So this is just SN2, and the solvent is reinforcing that. Solvent, polar aprotic. This is for real this time. I won't erase that A this time. Aprotic also favors SN2. We are like an SN2. And 2. And I don't have a stereocenter showing. I know it is a stereocenter. So I will write down 50-50 R and S. No, I won't. I don't know what to write. And that should be blue. Without a starting stereocenter, I don't know. If this was S, this would be R, because that's what SN2 does. If this was R, this would be S. And there's no other products here. Just these two, this one product, SN2 product. And our final mini topic for today, and I say mini, and yeah, we'll get done a little early, is E1. E1 is never the big deal. E1 is always a minor reaction every time SN1 is predicted. Burn this into your brain. E1 also involves carbocations. Remember, I hinted before, if there was a 1 in its name, carbocations are on your brain. Okay? So after carbocation formation, every so often, instead of the nucleophile attacking the carbocation, the nucleophile, oh, that's tough upside down, abstracts a beta hydrogen. Yeah, that's an elimination, by the way, if you're taking a beta H. So normal analysis would happen here. And you're going to predict SN1. Please, that doesn't change. E1 is just something you're going to add on at the end. It's like an afterthought. Rx is tertiary. This thing knows how to do nothing except for SN1. The only thing that can change my mind now is if I have a strong base in heat. And you're saying cyanide, is that a strong base? No, it's not. Yeah, I know I have heat. Caution. I'm going to put a caution here. This is a slow reaction. Some reactions need heat just to speed them up. Heat without strong base. It just speeds up the reaction. And I'm just going to tell you a fact here that you didn't know. Fact. HCN pKa ballpark 10. Therefore, CN minus pKb. Good review exercise. What do you got for pKb? I'll give you 2 seconds. Take a tea break. I got 14 minus 10. What's that? That's 4. Is that negative? 4? Not a strong base. Okay, so you're not doing E2. Blue new. New, strong, it's cyanide. SN2. You can't make a tertiary carbon do an SN2. 3, solvent, CH3CN. That's this one, acetonitrile. Polar aprotic again. SN2. You're not changing that tertiary carbon's mind. So you're just going to get an SN1. And it's going to look like this. It wasn't really a stereocenter, was it? Blue nucleophile. Oh, show pi. There you go. It's not RS to start with, so it can't be racemic. It would be racemic if it was a stereocenter. So why are we putting this in this discussion of E1? E1. E1 is always a minor reaction every time SN1 is predicted. Okay, so here's the E1. E1. The mechanism starts like this. How many carbons we got there? 2, 4, 5, 2, 4, 6, 5, 6. Is it a bromine? What's a bromine? It's leaving. Why? Because you predicted SN1. First step is make carbocation. Nice carbocation. All right. Normally, what's going to happen next? Cyanide, strong nucleophile, any nucleophile. It doesn't matter. You made a cation. It doesn't care. It says anything with a pair of electrons will do. I don't care if you're strong, weak, green, blue, purple, whatever. And there's your SN1. Right there. So starts off the same for SN1 and E1. Make the carbocation. SN1 finishes like this. Carbocation has other options. You really would prefer making a sigma bond, right? Well, this hydrogen went away as a beta hydrogen. Remember, the carbon used to be, this carbon used to have a leaving group on it, so still call that alpha. Alpha, what color? I don't know. And beta. And you can remove the H with cyanide. It's not a great base, so it's not itching to do this. You get very small amounts of this product. Always, E1, very small amounts. Grab H, make pi. Remember, elimination makes pi. Make sure you draw a pi when you do elimination, whether it's unimolecular, which is happening here, or bimolecular in E2. Make pi. Between what two positions? Alpha and beta. Okay. And you can also have the other product. Just go equals here too. And we have the cation here. Either one of these positions has beta H's as well. And you'll make even smaller amounts of this. And that would be the E1 from that position. And it looks like this. And in the book, it's, I don't know. The numbers in the book, I'm confessing now, were made up anyway. I think I used 95. I don't know, maybe this is 3%, 3.5%. When you're doing ballpark. How about 4? How about 1? There you go. So you're never going to predict E1 as a major product. If you have a test question where you come up with an SN1 prediction, but you have like 3 other product boxes that you have to fill out, guess what the other product boxes are? They're elimination boxes. They're minor. So that's what you do on the test. And I'm going to call that a week. I have an Orgo 2 exam later today. I'm almost ready for. And I wish you all the best and have a great, safe weekend. And I will talk to you on Monday, normal hours.